G'day and welcome back to Mathematics, the YouTube channel that takes band 4s and turns them into slightly higher band 4s. Thank you for joining me tonight as we dip our toe back into the Extension 2 course. I'm taking a look at some proof and inequality questions from the last couple of years of the HSC, going through 6 levels of questions. So we're going to start off nice and friendly and then work towards some more sickening and horrific questions. So let's get into it. Here's one from the 2023 multiple choice, and it's asking us, we have a statement: if an animal is a herbivore, then it does not eat meat. That is true. All right. Which of the following is the converse of this statement? Now, the reason I'm putting this question in this video is because there's been a question just like this in the last 2 years of the HSC. So the moral of the story here is that if you know your proof terminology, you can quite often pick up some free marks. So you should know your converses, you should know your contrapositives, know your negations. All that lingo is going to get you free marks most years. Okay, so for this one, all we need to know is that if we have a statement of A implies B, the converse of that is just reversing the direction of the logic and saying B implies A. So if you know that, we're just looking for if an animal does not eat meat, then the animal is a herbivore. And that is option D for 1 mark in the 2023 HSC exam. Okay, cruising so far, very easy. Let's step it up to level 2 of 6. For level 2, we have our first inequality question of the video, and we have 2 real numbers x and y, and x squared plus y squared is not equal to 0. Now for 2 marks, we're going to try and explain why this is less than or equal to 2. Okay, so with inequality questions, I like to start by just doing some rough working out and playing with the question and seeing if I can get the inequality towards something that I know would be a good starting point for my proof. So looking at this, I'm just thinking, well, why don't I start by multiplying the x squared plus y squared across to the right and then see where to go from there. I'm allowed to multiply that by that because I know that x squared plus y squared is going to be positive, so I can multiply throughout the inequality by that, and I don't need to worry about the sign turning around. Everything's going to be fine. So multiplying it across looks like that, and now I'm just like, why don't I just expand both sides and just see what happens? So expanding out the left-hand side with our perfect square, we get x squared plus 2xy plus y squared. And on the right-hand side, we get 2x squared plus 2y squared. Okay, now, if I bring everything over to the right, so I subtract x squared and y squared from both sides, and I subtract 2xy from both sides, I end up with this. So my 2x squared and my 2y squared are now 1x squared and 1y squared, with the 2xy over there on the right. Now, the reason that is fantastic news is because x squared minus 2xy plus y squared is the expanded form of x minus y all squared. And I know that x minus y always squared is always greater than or equal to 0 because a number squared is always 0 or bigger. So I've gotten to a point where I know that this is true, so I can start from here and then work backwards towards the target in the question to get my 2 marks. So that's my rough working out. Now for my answer, I'm going to have, this is my starting point. I'm going to expand it out, and then I'm going to add the 2xy across there, and now I'm going to make it look like this over here by adding x squared and y squared to both sides. So now the left-hand side is 2x squared and 2y squared, and the right-hand side is our expanded form of x plus y all squared. So factorizing both sides, I can factor the 2 out of the left-hand side, factorize my perfect square as x plus y squared, and now I can just divide both sides by x squared plus y squared to get the 2 by itself. While I'm doing that, I might flip the inequality around because I want the 2 on the right-hand side. So I end up with the target as required, QED for 2 marks. I've got to put the QED, but you get my drift there. All right, cool. So there we go. That's a pretty friendly inequality from the 2023 exam. There's going to be some much less friendly inequalities coming up later in this video. But on to next one, our level 3 question from the 2023 exam as well, is to prove that the square root of 23 is irrational for 3 marks. Okay, now, these questions involve quite a lot of work, quite a lot of steps, but as long as you've done some study and you've encountered these questions before, you should have a good idea of what those steps are and how to run through them. In case you're feeling a bit rusty, let's have a crack. Let's start off by, what we're going to apply here is a contradiction proof. We're actually going to assume the opposite of the question and then show that that does not make any sense. And if you need some more examples on how to approach questions like this, check out my contradiction proof video. Okay, so we're going to start off by saying, we're going to assume that the square root of 23 is actually rational. Now, the way you can write a number is rational is that it can be expressed in a fraction of 2 whole numbers and simplified fraction. So the fancy way of writing that in the Extension 2 course looks like this. We're going to say, assume, or there exists, that A and B are 2 elements of Z, so they're 2 whole numbers, 2 integers, such that the square root of 23 is equal to a over b, where a and b are co-prime. What that means is that a and b don't share any factors, so this fraction has already been simplified, yada, yada, yada. Okay, so this is us saying root 23 is a rational number because we can write it as a fraction. Okay, and now the goal of the question is just to really show that this equation here does not make any sense, and there's a very clever way of showing that. What we're going to do is start off by squaring both sides of this equation. So the left-hand side is now going to become 23, and the right-hand side will be a squared over b squared. So squaring both sides, we're going to multiply b squared across the left, so we get a squared is equal to 23b squared. What this is now telling us is that a squared is expressed as a product of 23 and something else. So this tells me that 23 is a factor of a squared, which means that a squared is divisible by 23. Now, fun fact about square numbers, if a square number has a number as its factor, or is divisible by that number, the square root, which in this case is a, is also going to be divisible by that number. So what I mean here is that if a squared is divisible by 23, it tells me that a is also divisible by 23. And the way we're going to write that is we're going to say a is equal to 23 times something, and that k is just an element of the integers, just like a and b. Okay, so a squared divisible by 23 gives us a divisible by 23. Lets us write a like this. Let's now make some room and put that into our equation up here. So instead of a squared, we're going to write 23k squared. So the right hand side, we're going to get 23 squared, not scared, I'm scared actually. And then we have k squared. What we're going to do is we're going to divide the 23 off the left hand side to get b squared by itself. And now 23 squared divided by 23 is, would you believe, 23. So what this now tells me is that b squared has 23 as a factor, so b squared must be divisible by 23, which then also tells me that b is divisible by 23, and that's kind of where our proof starts to collapse in on itself. We just explained that a is divisible by 23 and b is also divisible by 23, but the setup of our question to prove that this was rational is that a and b did not have any common factors because it is co-prime. What we've just shown is that 23 is indeed a common factor, which means that this does not make sense, and it's because our original statement did not make sense, because root 23 is not rational, and therefore the original statement in the question has been proved by contradiction. And that's the little yapping that you want to do in your concluding line on the end. As you can see, I've run out of room and I can't be bothered, but basically you want to say that because we've just shown this does not make sense, this does not make sense because this is true, QED, and then, you know, applause and move on. Okay, that's the fun half done. That's levels 1, 2, and 3. Now into the more spicy section up to level 4. We have a question from the recent 2024 exam. We have a 2-mark question. Prove that if a is any odd integer, then a squared minus 1 is divisible by 8. Okay, let's take a breath, do some stretches, and get into it. Okay, let's start off by showing that a is an odd integer. The way that we write odd integers in this course is we write them as multiples of 2 plus or minus 1. Okay, so let's just say a is equal to 2 times something plus 1, where that something is an integer. That is our setup for an odd number. Okay, let's put this into our expression. So we have a squared minus 1, so we have 2k plus 1, all being squared, with a minus 1 on the end. Okay, let's expand this out. So we have 2k squared is 4k squared. We're going to multiply them together and double it for 4k. And then we have 1 squared is 1, which is going to be cancelled out by the minus 1 on the end. So that's just going to leave us with 4k squared plus 4k. Okay, now what can we do with this? We can do a little bit of factorizing for feeling fancy. We can take the 4 out the front, and we can also take the k out the front, leaving us with 4k and k plus 1 as our factors. Now, when we get to this point, we can quite clearly explain why this is divisible by 4, because there's a 4 at the front, but how are we going to show that this is divisible by 8? I'm not seeing any 8s hanging around. So for this entire thing to be divisible by 8, I need k times k plus 1 to be divisible by 2, which would then multiply with the 4 and make an 8. So the harder part of this question is how can I explain why k times k plus 1 is divisible by 2? Okay, so the thing we have to realize here is that k and k plus 1 are consecutive numbers. All right, that means they're one after each other on a number line. Now, why that's significant is because if you have two numbers that are consecutive, that means you're guaranteed to have an odd and an even number, or an even and odd. Either way, k times k plus 1 is a product of an odd and an even number in either order. All right, and that's good because we know the setup of odd and even numbers from before. We can use a similar setup to then get some 2's in there, to then hopefully get a 4 in there, to get an 8 down here. So we're going to say that k times k plus 1 is a product of odd and even numbers. So let's just say that we have k is equal to 2 times something, where m is an element of the integers. So for this one, I'm just going to say k is the even part, and that's going to make the k plus 1 the odd part. So we have k times k plus 1 is 2m times 2m plus 1, because this is an even times an odd. All right, now this is cool because at the front of this whole thing is a 2. So I can put the expression for k times k plus 1. I can chuck it down here with my 4, and now I have 4 times 2m plus 1. And I'm just going to pull the 2 out the front with the 4 and make it an 8. And now I have 8 times something, and I can just say this is 8 times something, where that something is a whole number. And then I've shown that the original expression, which is a squared minus 1, is equal to 8 times something, so it is therefore divisible by 8 for 2 marks. Okay, moving on to level 5, we have another inequality question. This one's pretty nasty. It is known that for all positive real numbers x and y, x plus y is greater than or equal to 2 times the square root of xy. Do not prove this. All right, Nessie, you don't have to tell me twice. All right, this one's from the 2024 exam. It's worth 3 marks, which is a hefty chunk of your exam. We have that if a, b, and c are positive real numbers where the sum of their reciprocals is equal to 1, then we need to prove this expression here, which frankly looks like a bit of a mess. So we have 3 things here. We have 2 things provided to us from the question, and we have 1 thing that we're trying to show for 3 marks. So let's make a bit of space. We have the do not prove this, and this is some info, and we're trying to show that this green thing here. Okay, so where would I naturally like to begin this question? Well, the info that I've been given about A, B, and C is currently not very helpful to me because we have a relationship between 3 fractions. The thing that I'm trying to prove towards does not have any fractions. So I'm thinking, why don't I start off by re-expressing this blue equation here without using any fractions and then see how it compares to where I'm trying to get to and where it compares to what I've been given to use. So the way we're going to get rid of the fractions is we're going to take both sides of the equation and multiply everything by ABC. That's going to make the first fraction cancel out the a's, and we're going to get a BC here. We're going to get an AC in the middle, and then on the end we're going to get an AB. The right hand side is now ABC, and that's great news because if I look at my target, the right hand side of the target is ABC, so I'm probably on the right track here. So simplifying our fractions, we get BC, AC, and AB equal to ABC. Okay, now the trick with this question is how can I get this inequality in red over here involved to get some square roots into my expression and then get my 3 marks. So we're going to try and use the form of the x plus y is greater than or equal to 2 root xy. And we're going to try and get these BC, AC, and ABs involved. Okay, now when you're trying to relate 3 things adding together into an inequality where there's 2 things adding together, usually that means you're going to have to make a few different versions of the same inequality. I'll show you what I mean. If I go over here and I say, well, if x plus y is greater than or equal to 2 root xy, if I did this with a, b, and ac, which are 2 parts of my equation over here, well, this is going to be greater than or equal to 2 times the square root of their product. So 2 times the square root of ab times ac, which is a squared bc. Now that's cool because if I separate these out, the square root of a squared is just a. So this turns out to be 2a root bc, and flipping it around, put that on the left, we're going to have that less than ab plus ac. Now this is fantastic news because over here I see an a square root bc, so I know I'm probably doing something right. But the thing is, I need 3 more versions of this. So we're going to have to use this red inequality 3 more times to create 3 of these that I can then build towards my green equation. Okay, so that one was an AB with an AC, so there was A happening twice. Let's get this B1 in the middle by picking something where there's B happening twice. So I'm going to grab the BC and the AB and feed them into my red inequality over here and see what happens. What we'll see is a similar result. We're going to end up with 2B times the square root of AC with an AB BC over here. Okay, so don't need to do that middle step again because I can see where it ends up. I can basically say that the number that's by itself over here is the one that's occurring twice in the sum over here. And building the third one with the AC and the BC, so there's 2 C's on the right, which means we're going to have a C outside of the square roots on the left. And now I've got these 3 inequalities ready to build towards this green thing. Okay, so to build the green thing, I'm going to have to add all these together because I clearly want to have the 3 square roots summed together. So if I take the left-hand side of this inequality and I add them all together, I'm also going to have to add the right-hand side of the inequality together. So I have the AB plus AC. So adding these all together, there's two ABs happening. There's one here and there's one here. There's two ACs here and here, and there's two BCs here and here. So summing the three right-hand sides of these inequalities, we get 2AB, 2AC, and 2BC. Okay, now I've got a lot of 2's everywhere. 2, 2, 2, 2, 2, 2. Let's just cut everything in half. So we get this. Now on the right-hand side, what do you know? We've got AB plus AC plus BC, which, as we established from the fraction, is equal to ABC, which was the target for the right-hand side. So we sub that with that, make the right-hand side ABC, and then there you go. Beautiful 3-mark inequality proved. Wasn't that a lot of fun? I know he said level 5 was going to be tough, but I actually really thoroughly enjoyed that. But that's where the joy ends, because now we're up to level 6, which is a band 6 question from the back end of, QED. Level 6 from the back end of the 2023 HSC exam at an E4 level, so highest possible band for this question. Okay, this question was 5% of that year's exam. Part I is to prove that x is greater than log x for positive values of x. And then if we've done that, we can hopefully use that to prove this scary looking inequality in part 2. Okay, so this one is scary looking, but I honestly think it's a lot of fun. So let's take you through my thought process. Okay, for the first one, x is greater than log x. Well, if I do a sketch of y equals x and I do a sketch of y equals log x, I can see that y equals x is above log x. But I can't really do proof by diagram for this question because it's not very technical. So what I'm going to try instead is I'm going to think about, what about if I bring the log x over to the left and look at x minus log x greater than 0, okay? I kind of have an idea of what that graph looks like because this is log x, right, like this, okay? Cool little logarithm graph. So negative log x is just the flipped version of that, which looks like this. And now I want to think about what x minus log x looks like. So x looks like this, minus log x looks like this. If I add these two together, I'm going to get a curve that looks something like this, okay? Because this one is growing faster than this blue one is becoming negative. Okay, so this is my theory of what x minus log x looks like. I'm hoping it's a curve, and I'm hoping it turns around somewhere and always becomes positive based on my knowledge of what a log curve looks like and what the line y equals x looks like. Now, unfortunately, this sketch will not do, even though it is very beautiful, but we need to prove this. So how we're going to prove that this is greater than or equal to 0 is we're going to use a little bit of calculus. We're going to find out where this curve is turning around. So we're going to find a minimum turning point. So actually, we're just going to find a stationary point, and then we're going to show that it is a minimum turning point, which means that the curve is always above this point. That's going to be a fun little way to get 2 marks and explain why this thing is always positive. So let's do that. Let's start off with our function x minus log x, and let's take our first derivative. The derivative of x is equal to 1, and the derivative of log x is 1 over x. So there is our derivative. Okay, stationary points, we want to see where that is equal to 0. So that's where 1 is equal to 1 over x. And that very quickly and easily solves to x equal to 1. To get the y coordinate of our turning point, we'll take that and put it back into the function and say 1 minus log of 1, which is 0. So we have 1 minus 0 is 1. So our turning point's location is 1, 1. Okay, now to assess some concavity, we'll look at the second derivative. So taking our first derivative, which was 1 minus x to the power of negative 1. Taking the second derivative, the 1 goes to 0, the minus 1 comes down the front and makes this positive, and now our power is minus 2. And another way of writing that is 1 over x squared. Now, crucially, x squared is always positive, so 1 over x squared is always positive. And this tells me that if the second derivative is always positive, then my theory about the picture was correct, and this thing is always concave up. All right, so if we're always concave up, our minimum value is 1 for our y value of our turning points, and therefore, this function, x minus log x, is always greater than or equal to 1, which means it's definitely greater than 0. So our function is greater than or equal to 1, which means that x minus log x is always positive, and there's the first part done for 2 marks. Okay, let's see how that is useful in part 2. Part 2 is to show that for all positive integers n, e to the power of n squared plus n is greater than n factorial squared. All right, looks like a lot of fun. All right, what can we do here? Well, if we think about part I was a relationship between x and log x. So how can I get this involved in this proof here? Well, because there's a e to the power of on the left-hand side here, why don't I start off by taking the natural log of both sides of the inequality and just see what I'm dealing with. So taking ln of the left and right hand side. Okay, let's think about this. I have a log of something with a power, and because I passed year 10, I know that I can put that log power out the front. I also know that on the left hand side, the log and the e to the power are going to cancel each other out and leave me with n squared plus n. So there's my left hand side, there's my right hand side. 2 times log of n factorial. Now n factorial, of course, looks like this. Now, what can I do with logarithm of a lot of things multiplying? Hey, I can use my log laws here in reverse because I know that log a plus log b is equal to log ab. So if I have a log of a bunch of products, I can split that into a bunch of log sums like this. And hey, this is good. I now know that my goal for the right hand side is to create a lot of logarithms and add them together. I can do that with my starting point that I proved in part I. So there's my idea. Let's have a crack at it and see if we can build towards the left-hand side of n squared plus n. Okay, so starting off with 1 greater than log 1 because 1 is greater than 0. Similar thing for 2, similar thing for 3, so on and so forth, all the way down to my final value, which is going to be x, which is greater than log x as we established. Okay, now we're going to add together everything in these inequalities. We're going to say 1 plus 2 plus 3 all the way up to x is greater than log 1 plus log 2 all the way up to log x. Actually, I should have done log n here, but you get what I mean. Anyway, so summing up to n is greater than the log sums up to log n. Okay, now on the right hand side, I know what I can do here with my logarithms. I can combine them all together in 1 and do 1 times 2 times 3 all the way up to n, which is going to be n factorial. What can I do on the left hand side? How am I going to explain why 1 plus 2 plus 3 up to n is n squared plus 1? Well, fortunately on the left hand side, the difference between each term is consistent. It's always a 1 gap between them. So this is an arithmetic series, and this is why it's important for the Extension 2 students to know their advanced content because it can come into a high level question like this. So a formula we can use here to take the sum of a arithmetic series is a little shortcut formula. You can do n divided by 2 multiplied by the sum of the first and the last term. Okay, this is one of the sum of an arithmetic series formulae. So n is our number of terms, which is n. Our first term is 1 and our last term is n. So putting that into our formula, we have n over 2 multiplied by 1 plus n. On the right hand side, we're combining our logarithms all together by doing a product of 1 times 2 times 3 all the way up to n, which is of course equal to n factorial. Okay, so we have log of n factorial there. We're going to multiply both sides by 2, so the left hand side is just n times 1 plus n, and the other side is 2 log of n factorial. Now we're pretty close to where we want to be. We're going to put that thing in the front of the logarithm up into the power, and we're going to expand this into n plus n squared. Okay, and now one final step is to take our inequality and raise both sides to the power of e, and then the left hand side becomes e to the n squared plus n, and the right hand side will get rid of the logarithm and leave us with n factorial squared as required. I can't believe I didn't do the last step. That's so lazy. Anyway, you go from here and you do e of both sides and you get that, which is our target for 3 marks, and hopefully that's a good enough of a conclusion for you. Okay, that'll do it for this video. Thank you for choosing to spend your time watching my videos. I appreciate it, and I hope I'm helping your HSC. I look forward to helping you in some future videos before your HSC. But goodbye for now, and all the best for your study. And of course, don't forget to leave a like because apparently it helps. And if you are stuck on any questions, flick them to me on Instagram and I'll help you out to the best of my very limited ability. All right, ciao for now. See you soon. Adios, goodbye. Thanks for the memories.